All right, folks, we're now going to start working on Module 2 labs. If you were here right before the recording started, I did in my file system here inside of Windows, I created a folder for the labs. It also appears here in the Explorer area of Visual Studio Code, which you can trigger with this icon. And all my code will be stored inside here. So I'm going to make sure that this is highlighted before I create a new file. And so since we're going to be going right into the first lab, I'm just going to come up here to the toolbar and click new file. You can also do it from the file menu. And I'm going to name the new file mod2 lab1.py. Press enter. And now I have a blank Python file here ready to go. Next, I'm going to jump over to our core shell in Canvas, and I'm going to navigate to module 2 to get started. You will notice that I just released module 2 today. What I will be doing, by the way, for module 3 is that will be released before the end of the week. So you guys are ready for next week. We're going to click right into this first lab, and this one's called the area calculator. But before we dig into actually doing the functional tasks of this lab, we got to talk a little bit about the stuff we're about to learn. And we're going to learn kind of a very special little feature within programming, which is basically this concept of taking blocks of code and reusing them, right? Like if you've created something already, why would you recreate it later? You know, and retype the code from scratch again to do the same task that you've already created before, right? That's really kind of the grand takeaway here. And then we're going to also learn that this is really kind of a clever way to kind of arrange and organize your programs so that they operate more efficiently. And I'm going to say that the reusability of code is one of the most profound, really kind of developments in coding in the last 40 years, right? So like originally when people would write code, they would have this super long sequence of instructions. And then if they wanted to repeat part of that sequence, they would just basically recreate it farther down in the sequence, right? And then somebody recognized, well, wouldn't it make a whole lot more sense if we could just go back to the ones we already typed and just redo them again? And in the old days, we had ways to do that, but it was not very elegant. I'm not sure exactly when this happened, probably, I think in the late 70s, early 80s sometimes, they came up with this concept of reusability. And it applies to a lot of different things, but you'll see what I'm talking about. The construct that we're really going to be working on predominantly is a thing we call a function, right? So I'm going to W3 schools right now to kind of give you a little background on this. But basically, as they say here, a function is a block of code which only runs when you call it, right? And that's a really important line, by the way, because you can create a function and then you're like, man, I wrote the code, I hit run, and nothing's happening. All right, and then your instructor or your coding engine will come back to you and say, hey, if you want to really make it do something, you have to actually ask it to run. So just creating the function doesn't make it run. You have to call the function to make it run. So here's kind of an interesting piece of that. When we create a function, and I'll zoom in just a little bit more if that's helpful for you guys. We use this keyword, so we are defining. So this is the keyword def. Defining a function, you give it a name, and then you follow it with a set of parentheses. Sometimes you put stuff in those parentheses, sometimes you don't. It just depends on what your function does. At the end of that declaration, you use a colon, which basically says, well, everything inside this function follows, but I want you to notice a really key thing here. The lines that follow are indented. In this example here on W3 schools, they're indenting with 2 spaces. Now, the number of spaces that you use to do the indent is not a rule, it's a convention. There's a minimum of 2 spaces. Right? And therefore, all the code that belongs to this function has to be indented. Otherwise, it does not belong to this function. if you have the comparison of other languages that you've learned, let's say like C# or Java or something to that effect, even JavaScript, normally a function in those languages will be encapsulated in a set of curly brackets. And you know it belongs to that function because it's inside those curly brackets. Python doesn't use those. It only uses indenting to differentiate the code. All right. Now, you can define a function, but like I said before, it won't run until you call it. So even though I've defined it, nothing happens until I use its name to trigger it. Now I'm going to go to the try it thing here just to demonstrate and just to show you that I am actually creating something fresh. I'm typing in my nonsense characters here and I'm going to hit run. So this is calling it and it works. If I remove that and hit run, it is taking a long time for something that does nothing. Yeah, it's just, I don't know, it shouldn't really spin like that. But if you ran this in Visual Studio Code, you know, okay, well, it worked, right? Didn't do anything. Why didn't it do anything? Because I'm not calling it, you know? So you do want to call the function in order to make it execute. Even more interestingly, and this is the reusability of code, if you have the need to run this function a bunch of times, here's the power of this, right? I can run it a bunch of times. Now, granted, this is a very simplistic function, right? It's only executing one line of code. But what if it was 20 lines of code? With one command, you are now repeating 20 lines of code or calculations or output or whatever it is, whatever logic you want that goes into that function would be placed there. So that's kind of the advantage of using a function. Now, there's another aspect of using functions that's kind of interesting, and that is the capability to actually put something inside of those parentheses, and we call those either arguments or optionally parameters, right? So we hear both of the terminology here, and I will give you kind of a breakdown as to why we use one name versus the other. But basically, when we put something inside the parentheses, we are sending information to that function, which is then used inside the function to make it do its special task, whatever that task is. In this case, you know, in fact, let's try this, right? So this apparently takes what we think is called F name, I assume first name, and then we have like a goofy last name here. So they have, I'm not sure what that name is, but we could put in this and run it. And so then when we call the function, we are sending a first name into it, and then it concatenates it to Smith. So I have Emil Smith, Tobias Smith, and Linus Smith. Okay, very unusual names. I thought mine were weird, but those are even weirder, right? Or maybe not, you know, whatever. Weird names are cool now. As a kid, I always hated it, you know, by the way. Right, so that's kind of an example. Now, in terms of the terminology of this, the W3 school site calls this an argument. Now, it's an argument from the standpoint of where we send it from. So, in other words, when I call the function and throw something in the parentheses, the piece of information inside of it is an argument. When I'm at the function level, the information I'm receiving is technically called a parameter, and it's used internally. Now, what happens with programmers all the time is they interchangeably use that terminology. So they'll call this an argument and that a parameter, and I do it all the time too. And when you hear people say that, it doesn't mean they're idiots, that they just don't know the formal definition or kind of don't care. And you know what? Argument, parameter, you know, potato, potato, basically, you know. So think of it like that. But if you hear argument or parameter, it just means the thing that goes inside the parentheses for a function. Now, interestingly, what you'll notice is if this is a function, so it's a named block of code with parentheses that follow, does that mean that print is also a function? Yes, it is, right? And that's the first one we learned. And we also have learned input and float an int, and a couple of other things as well, right? So you begin to recognize that when something is named and it has parentheses after it, typically it's a function, or sometimes we also call them methods. And methods is really more a nomenclature for when you're applying it to a function that's part of a larger object, a more complicated object, like a class level object, right? And we'll get to that stuff too. So if you hear me say method by mistake, it means function, or some, that's another one of those words: arguments, parameters, potato, methods, functions, same kind of difference. They're still functions, basically. All right. That might actually be enough for us to kind of do our work now. But just remember that when you declare a function, that you still have to call it to make it execute. The advantage, of course, is that once it's defined once, you can reuse it many times. And when you become a programmer that's worked in the field a lot, you'll probably end up creating libraries of your own functions that you call into your own programs. I've done that a lot, especially programming websites and stuff. Where I came up with all these standard little JavaScript routines that I would use in all my pages. Or if I'm writing, like a piece of software, I have my own libraries I pull in, so I don't have to rewrite code that I've already created. That's kind of the interesting aspect of it. All right, back over to module 2. And what I'm going to do here at this point is I'm going to demonstrate a little bit of this functionality, just kind of from, let's say a common sense usability standpoint in terms of how you might use a function before I actually get into coding the lab. Now, before I take that step, I think this is a really good time to take a break. So I'm going to pause the recording here and we'll do a 5-minute break and then we'll come back and resume. All right, we're back from break and we're going to start working now on our Module 2 Lab 1. And I'm going to jump over to Visual Studio Code where I've already created a brand new file. If you wish, I don't really require this, but it's not a bad idea to maybe put your name at the top of the file. And maybe, if only for your own sake, list, what it is. If you named your file well, this might not really be necessary, I guess you could even go as far as putting the date on it, but files are also time stamped, so I don't really consider that necessary either. Now, a couple things I'm going to do is I'm going to drop in some information here incrementally, kind of in the form of notes, and I'm doing this to kind of reinforce the concepts. So when we create functions, the point of creating a function is to create code that is reusable. It's given a name, and we call it a block of code, and then we can also throw stuff at it. So that is, the first 3 things, right? So we'll use the definition keyword, we'll give it a name, and then we'll throw in some parameters or arguments, if you will. Then the other piece that we like to throw in as well is a colon, right? Well, not like to throw in, we have to throw in, right? Because that's like where it says this is where it starts. And then we have what we call the body of the code. Should be on the next line, I apologize. And then optionally, and then we didn't talk about this piece yet, the body of the code is indented. How far? Anandi, we were talking about that during the break. Maybe some of you guys caught that, but I'll go through that. And then optionally, depending on the kind of function that you're running, the function can, in some cases, return something back to the program where it was called from. And this often happens when you do calculations, for example. So, and if you notice what the name of this lab is, which is like a area calculator, we probably will send information back to the program. So we'll cover that piece, right? So this is kind of like the lay of the land. Now, to kind of demonstrate how it works, it's kind of nice to try one. We saw the thing from W3 Schools And I'm going to build one that's kind of similar to that, just a really, really basic one. So I'm going to build one called say hello. Now, you'll notice that I'm putting an underscore in here, and you could do it like this. So some people name their functions like this. So if there's logical words in the naming, they'll use an underscore to separate them. Or some will use what we call camel casing, right? And that's where you use a capital letter on each logical beginning word. You notice I'm not using it on the first letter because there's also a convention that if you're capitalizing something, it's an object or a class. That's not really a rule, by the way, that's just a convention. And that's true in most languages. So, I mean, which format you prefer doesn't really matter. I'm going to go with the first format for now. I'm not going to send any information in, so no parameters or arguments going in. But you'll notice here, as I type the colon, there's a little red underline, and it's like expected indented block, right? So like what it wants me to do is the next line of code, and I want you to watch what happens here when I hit enter. Notice it indents. On W3 schools, what I think is interesting, it only indented 2 spaces because that's the minimum required. But Visual Studio Code indents 4 spaces, right? Whatever your IDE does by default, you just go with it. But it did it automatically. So what I'm going to print or put inside here, I'm just going to put the statement, hello. Right, it's just one statement. Now, in order to make this work, now you notice this is kind of weird. All right, I press enter because I want to get out of here, but I'm still indented. If I want to actually call this function, I have to backspace to the margin and then call it. So for example, if I want to say hello with parentheses, that will call the function and make it run. And what you should do at this point is you should hit that run button, and let's try it. Let's make sure it works. Let's see, it said hello. It's all about the reusability of code. So if I paste this in a few times and run it, you will notice it will output it a few times. Now, going back to the thing we were talking about during the break, what if I need my function to have more than one print statement? Well, you can do that. So for example, or more than one line of code, right? So for example, I could have it print so I can have a separate statement that says that. I can also maybe even set up a variable. It's taking the calculation, and then I could print the results of that calculation. And then when I run the program again, right, and I'm going to scroll the code up so you can see it here and see the output. Now, every time I run it, it's going to do all of these statements all at once. So watch the output, right? Hello, you are in a Python class right now. 6, hello, you're in a Python, so it just repeats it. But the point is, it doesn't matter how many lines of code are in there, you can repeat all of them. And now you can get to see where it's actually more powerful. One line of code as an example, I think is kind of a weak example. Multiple lines of code, well, now we have some real reusability going on, because with one statement, I'm repeating all of these lines of code. That's the power of a function. Another aspect, right? And I'll throw in some comments here. If this is helpful for you guys, maybe it is, maybe it isn't. Right, so using a function, you call it by its name with any arguments to fulfill parameters. All right. Now I'm going to move on, and I'm going to define a new function. And this one will actually have some parameters in it. So for example, I'm going to define one and call it say hello to someone, parentheses, colon, but I want something inside here. So I want to pass in an argument to a parameter, and I'm just going to pass in somebody's name. And then on the next line, indented, of course, I will do a print statement. I'll use the print F in this case, and I'll say, hello, whoever the person is. So there's a function defined. Now I'm pressing enter again. I don't want to be indented at this point because I want to call the function. So I have to backspace to the margin to be able to call it. And first I'll put in a comment. And then, okay, I'm going to backspace again, still thinks I'm inside the block of code. I will reiterate a few calls to it. So this is all a copy paste on my part, just to accelerate this a little bit. So I'm saying say hello to someone and then put in different names. And you can call this as many times as you like, by the way. So I'm going to go ahead and run this. So in the console now, in addition to all of this output, you will see some additional outputs. I'm going to try to keep that on the screen there. So here you go. Here you are. Right. So Takis, hello Alex, hello Matt. And this is an example where we're passing information in. Now, what if we have a function where not only are we going to send in a parameter, but we also want to return a value. So now I'm going to define a function called get plus 5. And then what am I going to pass in? I'm going to pass in some number. I'm not sure what that number is going to be. It's going to be a variable. And then every time I run this, I want it to do some math. So I can do this two different ways. One way would be I could come up with a variable called answer and then take the number and add 5 to it. And then return, and here's a magic word there. This is return value, answer. Right? So I do the math, I store the result, and then I return the answer. That's one way to do it. You know what? We should run this so you can see kind of the output of this. So for example, I can, and I'm going to do this right in the print statement. And I'm just going to say get plus 5 parentheses 10. So I'm going to throw 10 into it. It's going to return it, the answer, right back to this spot and put it on the screen. All right, so watch this. So it took this value of 10, sent it to the function here. We added 5 to it, stored it in a variable, and then returned that variable. That ended up in this spot, and then we output it to the screen. That's one approach. Another approach, and here I'm going to comment this stuff out. Another approach, and experienced programmers tend to go to this approach, by the way, is they just go directly to a return statement. You know, who's to say that I need to store it in a variable? Nobody, right? If I need that for later, sure, store it. Otherwise, I'm wasting memory in the computer program. So why do that? We're just going to do the calculation and return the amount directly. So the return statement can actually contain the mathematical equation. I'll run it again and you'll notice the result is still the same. Still get 15 coming up. Right. So, you know, I would call this up here, I'd call it like one way with a stored value. Direct without storing anything. Your choice which approach you take. Neither one is right or wrong. It's just a matter of, you know, seeing, you know, what the usage is overall. Another thought here, and this is kind of a, a kind of an interesting one, is what if, and we haven't done this yet, but you can totally do this. I can call this function, and I could like hard code a value here. I could pass in a variable, but I could also put in an input statement where I prompt the user and say, enter number. And in fact, if I'm going to do that, I have to also convert it to a number. An integer would be a good one to do. And let's see, do those all match up? Yeah, one set, two set. You see how like Visual Studio color codes them? So yellow ones, blue ones, purple ones, and it put the second blue one in automatically. So I'm going to prompt the user, have them enter a number. It'll get sent to a function and then print to the screen, all in one statement. Talk about efficient, right? Let's run this one too. Oh, looks like I'm missing one parenthesis. Right, there we go. Right, so you notice the little red squiggle I had there? I'll control Z that. See that? That one's red, little red squiggle, just telling me I'm missing it at the end. So just typing it in. Here comes the run. Right, so enter a number, 4. Right. 4 plus 5 is 9. Now, this is not a bad approach, really. So now wrap your head around this. We have a function inside of a function inside of a function inside of a function. You guys got that? It's pretty slick, right? What I love about Python is it makes it so easy to do stuff like this, right? I could do it a number of different ways. So for example, I could prompt the user and convert the number and store it in a variable and then send the variable inside the function call as an argument. That would work too. Once again, it comes back to the issue of like, do you want to store the value or not? Kind of an interesting thought. Right, another thing that happens sometimes is and here's where we start switching into the regular assignment here, by the way. Sometimes we have more than one piece of information that we need to send into a function. So for example, if we're calculating the area of something, right? And typically when we think of an area, we think of a rectangular space, right? How do you calculate the area of a rectangle or square? Well, very simply, you multiply the width times the height, or the length times the width, whatever terminology you want to use, right? It's basically 2 dimensions. And by multiplying those 2 things together, you have the area. So I'm going to write a function now that addresses our homework, right, our lab. And I'm going to define a function called get area. I'm going to pass into it both the length and the width, spelled correctly, and then put in a colon at the end. Now notice what I did here. I'm really setting up 2 variable constructs with a separator of a comma. So I'm passing in 2 pieces of information. Now, the important thing here is when I pass in the information has to come in the relative order that it's being asked for. So in the definition of the function, length comes first, width comes second. I mean, in this calculation, it really doesn't matter, but in some calculations, it matters a lot. Like if I had a calculate mortgage payment function, I would want my principal to be in the right spot, my interest to be in the right spot, and my number of payments to be in the right spot. So I'm going to go ahead now, get into the function. And what is the calculation? Well, it's very simply length times width. I'm not going to store it. I'm just going to do a return statement, and I'm going to multiply length times width. That's the whole function. Now, it's really common, by the way, like when you're writing functions like this, that there's kind of some basic rules of programming, and they're not really rules. Okay, so I should really correct that. In programming a lot, we operate by convention, like what is a good way to operate as opposed to what you're supposed to do. And usually a good way to operate is when you write a function, for example, that does a calculation like this, that the function only does that calculation, right? I could display the result of the calc. I could put a print statement in, right, and display the result of it directly. But it's better that the function just does the math and we handle the output somewhere else. That way, if I ever need to reuse my get area function, I don't have to worry about changing the output part of it, right? I just use the math part. Hey, I have a get area function that just works, and you just drop it into any program where you need it, and it's there. Now, here's where it gets kind of interesting. So if I want to call this, right, I would typically, I'd say get area, and then I would send in, for example, 10 by 20. All right, now, this is kind of interesting because if I run this, I'm going to run it and show you what happens, right? Well, okay, so it's prompting me for the previous thing. So it did all the stuff we did before, you noticing, but I made it do this. Where's the result? This is kind of interesting. This returns a value, but if you're returning a value from a function, it has to have somewhere to go. Our most current example has us put it inside of a print function. So that's one way, right? So if I run this now, I'm still getting prompted for that previous thing. Now it will return the value because it has somewhere to go. Where? Into a print statement. Another option is I could set up another variable. I could say area equals the result of this function running. So in other words, since this has a return value, remember, anything we do on the right side of the equal sign gets stored on the item in the left, and then I can output that area. So here's the run on that. And you'll see that the math is correct. All right. Now, if you look at the lab description here somewhere, so create an get area function that does the following: accepts two parameters, returns the area by multiplying the two parameters. Create a calculate area from user function that does the following: accepts no parameters, gets two float inputs from the user, calculates the area using the previous function, and prints the result rounded to the hundredths, and then run this 3 times. So they have an example output. Now, we have all that other stuff that's built into our program, so it's okay that our program outputs that. But if you wanted, and I'm just kind of throwing it out there, all the stuff really that's, above here could be removed, right? I'm going to leave it in because they're examples. So, take that for what it's worth. But in terms of your homework, you might choose to remove it. So if you want, if you want to remove it, all you have to do is comment it out and just put the pound sign in front of it. You have to put that pound sign in front of all the lines of code, though, right? Some IDEs have shortcuts for this. Does anybody know what the shortcut is for Visual Studio Code? I think you just highlight, right click, and gosh, I forgot how to do it in here. All right, so that's why I'm just doing it manually. That's why I asked. I don't remember. I know, like, if I'm in Eclipse, it's a certain keystroke, and Visual Studio, it's a certain keystroke. It's probably the same as Visual Studio, honestly. All right. Anyhow, I'm just going to manually comment all this out so the program does exactly what the screen says. Another way you can comment stuff out, by the way, is you can use a series of 3 double quotes like this to comment out an entire block of code. So that's another way to do that. So now I'm just eliminating all that stuff from running. And you know what? These were good examples too, but once again, this was an example. So I'm going to comment this out as well. Now I'm going to do what it asked. So I'm going to go ahead and define another function called calc area by input. And then that's not going to accept any parameters. And then what I'm going to do here is I'm going to need to ask the user for the length and the width. So I'm just going to come up with two variable names. I'm going to keep it really, really simple. L for length. And then I will be converting whatever I get to a float. And then I'm going to prompt the user. And I'm going to say, enter a length. Same thing with width. You notice how I'm doing that, you guys? Right. And you'll find your own workflow on it. I'm not like here to coerce you to type a certain way, but you find certain efficiencies. And real frankly, when you switch between different tools, each tool has its own workflow. Visual Studio Code is not a comfortable workflow for me. It's not a tool I use very often. Trying to acclimate to it because everybody seems to be using it. Then we're going to set up another variable called area. This we kind of tried above, right? And we're going to basically use the same approach, but we're going to say get area, and inside the parentheses, we're going to send length, comma, width into the function. It'll run it, return a value, and store it here. And then we're just simply going to output it. And we're just going to say print. We'll use the f-string method, and we'll say the area is area. Hold on. Now all that's really left is to call the function a few times. And I want you to kind of pick up on what's happening here. I'm going to be calling this function. This will prompt me a couple times, send it off to the other function for processing. So that tells you right there that one function can call another, and then return the result and put it on the screen. So I'm going to do 3 calls to this. So I'm going to call it 3 times. And here it goes. If you guys are following along. So I'm going to enter, I'm going to use really simple numbers so I know they're working correctly, by the way. So I'll put in a length of 5 and a width of 5. There's the area. Now it's prompting me again. Enter a length. Let's go 10 and 20. The area is still correct. Let's go 30 and 50. All right, so you can see all of them work correctly. The output that we're getting is in a floating point format, right? So it's always a point whatever after it. Now I was just entering integers, but okay, so I'll run this again just to show you. I could enter precise numbers. So I could do like one, something like crazy like that, and then get a very precise answer. And I'm just showing this as a demonstration, because who's to say that your numbers always work out perfectly? They rarely do, right? And the other thing you're going to start learning about Python is Python has this crazy capability of working with very, very large complex numbers without doing a lot of tweaking to it. So like if you're used to coding, for example, in C# or Java, where you have to think about that, like, oh, I'm going to put this in an integer, but an integer only has the capacity to hold a number up to like, 3 trillion or something weird like that. You don't have to worry about that in Python. And that's kind of telling, actually, because that's one of the things that makes Python so favored in data science and artificial intelligence, is because we don't have to worry about scaling our numbers. It just does it. And you know what? I could pump in much, much larger numbers and it just automatically scales. All right, so that's lab 1, folks. All right, now that we finished with lab 1 in module 2, we're going to move on to lab number 2. This one's a program, ultimately it's called the change calculator. And what I'd like to do here is that we have a couple new concepts to throw into the mix again. Now, when we work on programming, I'm going to kind of do this little sideline, and I think I did it last time. I actually pulled up one of my course shells from the other school where I teach, and yes, I'm logging into that school right now. I'm going to my course management system inside of there, and I do this little spiel with my students in that class that you guys don't really get here, but I like to do it for most of my students just so that you understand, kind of the basis of where we are in terms of the logic of programming. One really important thing about programming is programming is always about problem solving. And problem solving really is basically an extension of a branch of mathematics that we call logic. And it's really kind of like almost falls into like the philosophical realm, so to speak. But someone figured out a long time ago, well, a couple hundred years ago, basically, that there's three methods basically for solving logical problems. And that is you either develop a step-by-step set of instructions, right? Do this, do this, do this, do this. Sometimes that set of instructions requires that you repeat code. So enter functions and loops, which we're going to learn about soon. And then there's also this other branch called selection, which is basically branching in code. So like you ask a question, and then based on the result of that question, you choose one pathway or another. So you're driving down the road and the road splits into two. One goes to Chicago and one goes to Madison, let's say, for example. It's your destination. So you can't take both paths. You have to take one or the other. And, so there's kind of like a true false thing that happens when we get to selection. All right, so that's kind of the underpinning of it. And if I showed you this stuff before, I apologize, but I always like to kind of pin it down to some sort of like logical construct. So as we kind of move into this, it makes a little bit more sense. Now, ultimately, what we're doing in this program, and this is a very classic programming problem, by the way, is when you walk into a place and you pay for something, and this always amuses me to no end these days, because in the old days, everybody knew how to handle cash, right? Like you'd hand somebody, like you go to McDonald's and your total's like $6.59, and you give them a $10 bill and they knew how to make change. And now, if you give somebody a $10 bill and then you give them like 9 cents on top of it to kind of get around change back, they're like, they don't know what to do, right? But you can also use the cash register. Like the cash register has built into it, right? You type in the bill you receive and then you press enter and then it tells you what to give back. And then you have to break it down to quarters, nickels, and dimes. And so really what this programming problem is about is what is the correct algorithm for determining the correct change? And this very particular problem is responsible for a lot of kind of like some of the unique programming constructs we use in programming that, like where did modulus come from? Well, it came from this problem, by the way. Somebody had to figure out, what's the mechanics for doing this? And then, we came up with the mod operator as a result. All right, first, let's look at some documentation. So I'm going to take us off to W3 schools, and we're going to repeat the concept. We're going to be using functions here. So we are going to be calling functions in, do the work. So that knowledge is still pertinent. But we're also going to learn about if statements and, actually if else statements. And this is the branching piece of the code. This is where we're making decisions or making selections. And one of the classic little things I tell my students is like, a really good example for like an if statement, right? So I'll use silly examples like this. I'm hungry. I want to have something to eat, right? You know what? If I reach into my pocket and I find that I've got like $20 or more, or log into my bank account and say I got $20 or more, I'm going to order pizza from Pizza Hut and have it delivered, right? Because I can afford to do that with $20. If I have less than $20, then I'm going to make mac and cheese at home, or make a sandwich or something, right? So there's like kind of like you're making a decision. So that's a really good example of like it's dependent. It's dependent on how much money I have, right? Or you could also argue how much money I want to save, right? So it's cheaper to eat at home usually than to order out. So, however, when you're making those types of decisions, we often have to make them based upon what we call true false statements. And true false statements result in a value of the true or false, or what we often call that kind of a value in programming is Boolean. Why? Because there was this guy that invented the concept of logic and true false. His name was Boole. So when we came up with the concept of a Boolean value, it's a true false value. So for example, when we often come up with true false values, we do that based on comparison. So for example, if something is equivalent to something else, and I did mention this, right? The equal sign in programming is not the equal sign, it's the assignment operator. So the actual equal sign becomes a double equal sign. And so what the statement really says, if A is equivalent to B, now it's either going to be true or false. It may or may not be, right? But we're going to check and see. Or if they are not equal, notice the exclamation point. So the exclamation point in Python and in most other languages is what we call the negation symbol. It negates equality. So I could render something true. So if A was 3 and B was 2, they are not equal. Therefore, the statement is true. Weird, but that's how it works. You can also use the greater than and less than. So we can check to see if one is less than the other. So it might be like money in pocket less than 20, right? So don't order pizza. Or if money in pocket is greater than 20, order pizza. You can also throw in the equal sign. So like in mathematics, usually when we do like greater than or equal to, we put them like this, like over each other or under each other, like, and that should be familiar if you do math. But in programming, we have to separate them. And we use the less than or greater than symbol first, and then the equal sign. But when you use the equal sign, it's inclusive, right? So it can equal or preferably be greater. I know some of you guys already know this, but we do have people here that are brand new to programming. And these are really important logic pieces that you need before you go into if statements. Now, an if statement in programming is kind of constructed like this. So here's an example. Excuse me. So I set up a couple of variables, an A and a B. I assign A the value of 33 and B the value of 200. And then I check. If B is greater than A, which it is, then use this print statement. So let's just go ahead and try this, right? Get rid of my toolbar here. So if I run this, and actually we already had the answer in the screen. So B is greater than A. But what if I change the value of A to 333, and now that is, this statement is now not true, it's false. What happens? You can tell it's spinning for a while. Nothing's going to happen, right? It's not going to execute that code. I don't know why that the code that doesn't work takes so long to execute. I think it's because it's confused or something. But you can see nothing happened on the screen. Now, just to show you that the program is still working, right? I'm going to just do a print statement down here, just saying program complete, so it doesn't keep spinning. So if I run that again, it should go a little faster, I'm thinking now. Program complete, just doesn't do it. So what I could add here, and this is kind of the next part of the W3 schools example, is I can put in an else. So if B is not greater than A, then I'm going to print A is greater than B. And then we're going to test this so you can see the results. So if I run this, A right now is greater than B. So that's what it prints. If I switch the value back to 33, so now B is greater than A, the first statement will ring true, right? So basically what happens here, folks, you see the if statement uses the indentation thing. So by indenting, this line of code is what happens if this statement is true. I could add more lines of code, if that's a question, right? So it could run 20 lines of code here. If this statement is not true, it will go to the else. I don't have to check any logic. This code will just execute. So that's an if and an else. You can write statements that are if statements that don't have an else. That's okay. It doesn't have to have an else, right? Sometimes logic will dictate that. Other times, logic will dictate that you do have an else. And if you only have two paths to follow, Chicago or Madison, pizza or mac and cheese, for example, there's only two choices, and the first choice you test is not true, then the second choice is automatically true. You don't have to test it if you only have two paths. But if you have multiple paths, and I'm just going to demonstrate right here. I think it's easier to demonstrate here than inside of Visual Studio Code. We have what we call an else if statement, where I can check a different piece of logic. So if I say else if A is greater than B, then I will have this statement, because that's really the correct output here. And then there's a third scenario. So either A is greater than B, or B is greater than A, or they're equal. And because that's the only other option, I don't have to test for it. I can just say else. I can print, because logically then A and B are equal. So I'm going to test each one of these. So here comes the test. Right. In this case, B is greater than A, so that's correct. Let's switch it now. Make A greater than B. So second statement's true. And then let's make them both the same. And now you'll see that A and B are equal. I didn't have to test it because that was the only other option. So this,
what happens if you don't change the else statement and they're equal?
Say that again, Cody?
If you do not have the else statement in there and they are equal, what happens?
If I don't have the else statement in there?
Yeah, and
Okay,
they are equal.
So let's try it. Nothing happened because you didn't tell it to do anything.
Got it.
Interesting, right? Now, not to complicate things, but you can, and I'm not recommending that you write your code like this. You can also make these three exclusive if statements. Here's a chance where we can use the equal sign. So instead of having else ifs, this works too. This isn't as efficient though, right? Here's why it's not as efficient. Here I'm checking one piece of logic. It's either true or false. That's not true, then it checks the second piece of logic. It's either true or false. So if that's not true, I don't have to check again. If I do three separate if statements, or I do two else ifs, and yeah, in Python it's weird. They do elif. Sorry, they came up with it, not me. Other languages we say else if. I don't need to do a third check, and that saves one step of processing. And on computers, I'm just telling you, it's all about efficient use of storage, efficient processing. If I don't need to do another processing step, it saves a clock cycle, it saves a memory location, and your program runs faster. So I could write three separate if statements or two else ifs, but this is the most efficient way to do it. Now we're going to add a little bit of stuff to this as we go, but I do kind of want to get over to kind of working on the actual lab here. Find it now. There it is. All right. So I did want to look a little bit more on this. So they do make the point here, for example, if you don't indent your code, this is not part of the if statement here. It must be indented for it to be part of the code, right? Other languages, we use curly brackets or whatever to make sure it's part of it. And I think they do a little example of the else if, right? Very similar to what we just did. Right, so just to kind of reinforce. You can also do if else, or if else. And okay, which do you use and when? Okay, here's the answer to that. It depends, right? That's my favorite answer to everything, by the way. What, hey, which one do you use? Well, it depends. What does it depend upon? The situation, right? Because when you're writing code, you're trying to solve a problem. It's relative to which problem you're solving. So in certain situations, the logic will dictate that it has to be one structure or the other. Secondarily, can you have different logic structures that both correctly solve the problem? The answer is yes. Right? Now, would one be more correct than the other? I would say whichever one uses the least amount of code and the least amount of memory and the least amount of processing steps is the better answer. But real frankly, those efficiencies come with experience, practice, and time. And as you become more experienced writing code, you will see those efficiencies. And so, like, if you see some people here in class, like, very quickly coming up with their else if statements and whatever, it's because they've had experience in other languages. If you're brand new to programming, you'll be a little, more cautious, or maybe overly verbose when you're trying to figure out the logic. And that's okay. As long as the logic works, that's really what's important. Does it give you the correct response? And you saw that with 3 if statements versus if else, which was more efficient, right? And I think they keep going on here, right? And not to complicate things, but they have a third approach. And this is called what we, and I don't know if they label it here. They call it shorthand if. If anybody's coded in C#, and I assume there's at least a few of you that have done that class here, we call this in C#, we call this a ternary if, right? If you want the formal language on it, but it basically operates like this. It's one statement, right? And the statement still has the true false check, still has the colon, but we write it on one line. So when you have this, basically one possible result, you can put it in this format, because if the statement rings true, it's going to run. If the statement rings false, which I just changed it to, right, what's going to happen? Well, nothing is going to happen. And for whatever reason, it takes forever to do nothing. You can also ramp that up, and there's another level of this, and I don't know if they show it on the website, but you can put an else in there, and this is the implied else. You put a question mark in, and then you can put in, for example, print whatever. That's my favorite go-to, by the way, when I can't think of something. Once again, all on one line. This only works in the situation, though, where there's one line of code in the true part of the if and one line of code in the else part of the if. So watch it work now. So it should, oh, I didn't like that. So apparently I'm not in the right format here. And I know why. I think you have to do this. All right, let's see if my syntax is correct now. So I'm not doing the syntax right. So strike that, and maybe I can erase that from the video. I'm not using the right format here, but there is a format that allows, and I just thought of what it is. Okay, so you know what, let's go, we'll go back to that. And I don't know if they have the example here. Okay, so this is the correct example for it. So the format is basically this. Okay, so I'm sorry, I'm mixing languages, but basically you put the result ahead of the if. So you say print A if A is greater than B, else print equal sign, Right. So it kind of like cascades down. And you'll see the result of this one. This is kind of a weird one. All right. We'll come back to that one. Don't let that one confuse you. And I apologize if it did. It's not my intent here. Let's get into coding the lab. So once again, like we did about an hour ago, I'm going to start coding this. And then we'll get some of the work done basically, and then we'll take a break and give your brain, you know, a 5-minute break or whatever, and then we'll come back and finish it. All right. So let's read the instructions first. So we're going to create a calc change function that does the following: accepts one parameter representing an amount of money. Calculate and output the least amount of change using the following denominations: dollars, quarters, dimes, nickels, and pennies, you know, like basically what we're used to. So in other words, let's say you're operating the cash register and it tells you you have to return to the customer $2.98 in change. What's the most efficient way to do that? Now, if anybody's ever worked retail, and done it a lot with cash, and I, sad to say, like I grew up as a child working retail from the age of like 12 because my parents basically made me, and we didn't have a cash register or a calculator at that time. It was all like I had to be quick on my feet and I had to make sure I made the right change, because if the drawer was short, then they would take it out of my pay. Yeah, even as a kid, my parents would do that to me. But it did teach me very quickly how to correctly make change. Um, and I kind of do it automatically. I don't even think about it. But I am always amused at how young people that I absolutely can't, and why would they? Everybody pays with plastic, right? All right. So we're going to do that. If a denomination is not used, do not display it. Okay. Well, I'm sure I can do that with an if statement, right? We'll call that function with the appropriate argument from the user. So we're going to basically run it a few times is what we're going to say. Now, we could prompt the user to enter the money amount if you wish. We could hard code it. I really don't care about that piece. It's the mechanical parts that are more important to me. All right. Back over to Visual Studio Code. We're going to create a brand new file. So I'm inside the Module 2 Labs folder, and I'm going to click the new file. You can do it from up here too. So new file. I'm going to call it mod 2 lab 2. And see, my caps lock is on. I didn't even notice until I was already typing it. .py. You can name it whatever you wish, but doesn't it make sense to name it something like that? It sure does. Right, so there's the create file dialog. So here's my blank file. We are going to begin by defining our function. So we're going to call it calc change. We're going to send into it some amount of money. I don't know what it is. It's a variable. There's your colon. And then if it's helpful for you, and I'm just going to kind of give you a couple of tips here, you could also, add a description of function. All right. Now, there is kind of actually a standard nomenclature for this, or approach in Python, if you really get into it. So if you were like, for example, writing Python libraries, they use this really goofy format like this. That's not very good English, but there's kind of like this format that you do like this. So some people, when they write functions, create documentation, not only for themselves, but for any other programmer that might look at this in the future and go, what's this function do? What are the parameters? What do they mean? Because, okay, this is a very simple one and it's easy to understand because it's named well. But what if it's something like, I don't know, something like super scientifically complex that has 20 parameters coming in and does really sophisticated calculations, you know, or whatever, right? Documenting it is actually kind of helpful, right? So you don't have to do that, but it's a thought. Now, as we're going to build this function, we have to think about the mathematical mechanics of what we're about to do. So for example, if I have like an imagined amount of money coming in, and I'm just going to use this amount here because I've used it before for a program like this. This is really actually kind of an interesting amount. So let's $2.59, right? That's going to be my target amount. Now, I want to first, maybe it's a good idea to just, for the sake of the user, put some information on the screen and say, change for amount. So like, what are we, you know, doing this for? You know, which value are we doing this for? So it'll put that back up on the screen because I might hard code this. So if I hard code it, let's put that amount on the screen so I can see it and refer back to it and think about if it's correct. So that's just output to the screen. First, you know, if we're going to be basically building how many dollars, quarters, dimes, nickels, and pennies we're giving back, I'm going to create 5 variables with those names. Okay. Let's start with the highest denomination first. So for example, dollars would be a good one to start with. Right. So how many dollars do I want to give back for $2.59? Well, my brain says immediately 2. You know, and if I got hard coded, I would just type the number 2 here and be done with it. But how do I take that? If I send 259 in here, how do I take 259 and basically remove the 0.59? Okay, this is actually pretty easy. If I did division, so if I did this, if I divided amount by 1, it would return 2.59, right? I don't know if you guys remember this operator from last week because we went through this stuff so fast, but there's a double slash that's called floor division. And so I'm just going to add this in, floor division. So I'm putting it, making it for both so it makes sense. But basically what it does is it does the division, but omits the fractional portion or the 0.59, right? So opposite of what modulus does. Modulus returns the remainder. This returns the other, you know, how many times does it go in? You can also think of it as like rounding down if that's more helpful. So if I do floor division of 1 on dollars, that will return 2. How many dollars? 2. All right. Now, I think this is a really good place to take a pause for a break. We're at 8:07, so it's about an hour since we took our last break. So let's do a little bit longer break this time. Let's come back at not quite 10 minutes, maybe like 8:15-ish. So I'm going to pause the recording and I'll see you guys in about 8-9 minutes. So as I'm coming back from the break here, I had a question. Somebody tried running this and basically they got a, you know, the value dollars is not, you know, I don't know what the exact error message was, but you tried running this, but there's nothing to run yet. We're still defining the function. And if you do actually call it to run, right, and we send in a value like 2.59 and hit the run button, well, it's going to put that on the screen. That's all it's doing right now. There's nothing that we can see that happens. If I remove the function call and try running it, I'm going to assume I probably get the same error message. Well, actually it ran, it just didn't do anything. It's just blank, right? And the magic sauce really is calling it. So if you want, you could put in a function call right now just to have it ready. And then when we put in that test amount, we can see if it's working. Right now, there's still a lot more logic to type in before we get to that point. But there is going to come a point here very quickly that I will be running it just to see what it produces. So we have a basis of comparison. All right, so let's continue then and figure out the next step here. So we successfully, at least I think, right? We haven't really verified it yet, that this, at least logically, if I floor division one, you know, right, if you divide any number by itself, you get itself, but I want to eliminate the 0.59. So floor division would do that. Now we can test it. Here's a really primitive way to test it. Let's just put in a print statement and have it print dollars. I'm not worried about formatting or anything like that. Let's just see if it works, right? Am I getting 2 back? All right, so I'm going to run this and then look at the terminal down here. How many dollars does that result in? 2. Well, 2.0. Okay, so now why does it do 0.0? Now we're sending in a floating point number, so it returns a floating point value. This is kind of a really important concept too. This is a concept we call casting. Here, you know, we're dividing by 1, which is an integer, but the number we're dividing into is a floating point number. So I get back a floating point number because at least one of the numbers is a floating point number. Now, in other languages, like for example, if you're working in Java, like if anybody's like a Java person, Java doesn't work like that, right? It actually works very differently. So it's important to know these like weird little nuances of Python as you delve into doing calculations, because that way you can make your answers more correct. And we're going to encounter one of these problems coming up right now. And I've kind of prepared a little bit of an example here that I'll show you as we kind of move forward. So I'll have you think about where we're at with the process of this. So right now, we've really correctly determined, at least primitively, the right number of dollars we need to give back and change. 2 $1 bills, right? So in order to make sure that that's correct, right? So $2 are gone from the 259. So for the amount, then the amount needs to be decreased by that amount. So I'm going to take basically the leftover and I'm going to say, I'm trying to think of the most efficient way to do this. If, and this is kind of really weird because you could say, like, this is probably what your brain would tell you to do. Your brain would tell you to say, well, you took $2 away, so just subtract dollars from amount and then proceed, right? Because then you should be left with 0.59, correct? Well, yeah, you probably would. However, there's a more clever way to do this, and this is, like I said, this is where the impetus for modulus came from. So this is where it gets kind of interesting. Instead, what I really could do here is I could just say amount mod 1. So if I divide 1 into 2.59 and it ignores how many times it goes in and only gives me the remainder is what? It's the cents, 0.59. To prove that, I'll do another print statement here of the amount. So when I run this, watch what happens. Now, this is where it gets a little weird. All right, it should say 0.59. But what's happened? It says 0.58999999 repeating, which is really, 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 really close to 0.59, but it is not 0.59. Okay, and this highlights a really interesting problem in Python. And while I was on break here, I wanted to pull up like some sort of documentation on this. And what I did, right, is I just used Google and it brought back this first response. And this is basically happens because humans work in a base 10 number system, but computers work in a binary number system. And when you convert numbers from base 10 to base 2, there's inaccuracy that falls into place. So whenever you're converting number systems, there's something that's lost. It's kind of like converting audio from analog to digital. Something's lost in the process, and you convert it back to analog, so even more is lost. Every time you do a conversion, you lose a little bit of precision. And unfortunately, computers work with base 2, human beings work with base 10, unfortunately, because we have 10 digits, right? That's where that comes from. If we were born with like 2 fingers, it'd probably all be different, you know, or 1 finger on each hand. So that's the why. Now, okay, so how do we fix it? Right. Well, what we do then is we take this and we do a rounding correction. So we'll do this. We'll say there's a round function, and we'll wrap it around this value, but we need to still do the math, but we need to tell it to how many places we're rounding, which will be 2. Okay. And so I'm just going to put a little note here to correct the rounding error because of binary conversion. Right. Now, this is something you get to learn as a Python programmer. If you're a programmer in another language, once again, a lot of the tools in the other languages obscure this from you, but this is really happening in the background, even though you're not aware of it. Right? They wrote code to take care of it. In Python, we have to implicitly write the code. Not implicitly, explicitly write the code. We must write it. It won't happen automatically. Now watch the difference when I run it. Now I get the 0.59 that I want. So that combination basically of floor division followed by modulus rounded is the whole flow of the logic here. And so we're going to just keep stepping this down. Now for right now, I'm dropping in print statements so we can see if the amounts are correct. And then we'll go from there. So now that I've adjusted the amount correctly, now I'm going to determine the number of quarters. We're going to do floor division again. So we're going to take the amount that we have left. We're going to divide it by 0.25, which is the value of a quarter. Right. Now, if we have 0.59 left, floor division will divide into it evenly twice, and we should have 9 left over. So I can print quarters. In fact, let's try it. All right, so 2 quarters. That's right. Let's keep ramping it up. Now I'm going to do the adjustment to the amount. And what's going to happen here, folks, is I'm going to end up eliminating these print statements. I'm just putting them in here for testing purposes to see, so you can see what the code is doing. And then I'll probably just comment them out. And so now amount will once again be around the rounding of the amount. And this time, what am I going to mod by? Well, 0.25, but by the same thing I just divided by, once again, rounded to 2 decimal places. And when I print out, let's see here, print out the amount, I should have the right amount left now, which is 9 cents. If I didn't do the rounding, so I just want to show you this again so you see why we're doing it. I can run it. Then I get like this. Yeah, no, that doesn't work. I don't have that small of a denomination in my drawer. So that's why we do the rounding to 2 places. Right, so I think you see the pattern of it now. So from here on in, I'm not going to put the print statements in. I'm just going to keep ramping it up. The logic flows exactly the same way for all the denominations. So for dimes, we're going to take the amount, floor division by 0.1, and then the amount is going to be the rounded result of amount mod 0.1 rounded to 2 decimal places. And then the amount of nickels. This is a weird little sideline. I was going through this little collection of change that I had here the other day, and I found a buffalo nickel. I haven't seen one of those in forever. I don't know when they stopped making them, but kind of interesting. Probably not worth the coin is printed on. But. So for nickels, we'll divide by 0.05. The amount then would be the rounded result of the mod 0.05 rounded to 2 places. Do the same thing with pennies. And I know I'm going quick here, but remember, you guys can screenshot it and watch it in the video in the aftermath, so don't panic. Now, this is where it gets kind of interesting because I'm down to 0.01. I don't have to do floor division at this point. Like, you can do it with floor division, it still works. But there's enough precision left, is kind of the way to put it, that I don't need to round at this point. And I don't need to do any of the rounding at all. It will just be, it should be correct. So if you want to verify that, you could put print statements in here. In fact, maybe it's a good idea just for testing. Let's just run this and make sure it's doing the right stuff. So I'm going to print dimes. I'm going to print nickels. And I'm going to print pennies. So we're close to a solution here. I don't know if you guys are feeling it or not. I do see a question there. Jacob, you have a question?
I think you spelled nickels wrong.
Oh, you sir are correct, right? And I just kept rolling with it too, right?
Yeah.
At least I was consistent, bro. Thank you for pointing that out. All right, thank you. All right, I'm going to run this and let's just take a look at the console here and the output. And so, all right, this gets a little convoluted because dollars, 59 cents. Okay, so 9 cents. So how many dimes? None, no dimes, right? Because it's 9 cents left over at that point. How many nickels? 1. How many pennies? 4. All right, so we need to clean up our output. So we have to have print statements that say $2, 2 quarters, no dimes, 1 nickel, 4 pennies. Right, so but I think the logic is working correctly now. I am going to eliminate these print statements and I'm just going to comment them out. So I'm just kind of putting it out there. This is a really common usage for comment marks for programmers. Like sometimes we just throw stuff into the code just to make sure our calculations are working and it's doing what we're expecting, even though we don't really need that in the finished output. So I'm just removing all of that stuff. Okay, so all the print statements that I had are now removed from the code. If you want, you could just delete them. That's fine too. I'm leaving in there so I can see a trace in the future when I look at this again. I'm like, oh yeah, I did this because I wanted to show people something, right? If you want to remove those, that's on you. So now we've completed that step, but now come the if statements, right? And so what I'm going to do, these are going to be exclusive ifs. What I need to do is I need to check, does each one of these things that I just calculated have a value? In other words, is the value of this thing greater than 0? You know, like for example, I calculated $2. That's greater than 0. So if it's greater than 0, then I'll say $2. Feel what I'm saying with that? You know, so follow my logic here. So I'm going to say if dollars is greater than 0, then I'm going to print the following statement. I'm going to do an F string. I'm gonna put in how many dollars it is. I'm gonna say dollars. And then I'm gonna format it in the form of money. And because if you remember from that output, it was coming back as 2.0. I don't need to say $2.0. I just want to say $2. So I'm gonna put in a colon. I'm gonna say 0.0f, which means no decimal points after the decimal point. We get rid of the decimal point. And then some text, dollars. We'll say $2. Right? Let's just try it right now just to make sure it's working right. $2. There it is. Right now we just need to do the same for all the rest of them. Right? So that pattern that we just established, we're gonna apply that to, yes, I'm copy pasting. Don't tell me it's unfair. At least I'm giving you the answers. All right, so there's quarters. So if quarters is greater than 0, we'll put the number on the screen with no decimal places, and quarters with an optional S because it might be 1/4, right? At the most, how many quarters is it going to be? 3, right? It's the highest number of quarters you can have as change. 75 cents worth. You get up to $1, it's 4, and you just give them $1. Right. But see, if the change amount I put in doesn't require quarters, this won't trigger. There's no else to this. Same with the dollars and same with all of them. So if you follow that logic, then you can basically just tweak one of these statements and paste in the rest. You know, you just change dimes, right? Nickels. Spelled correctly, and pennies. So nickels is spelled incorrectly, but I'll fix it. See how it told me it was spelled incorrectly? And spelled incorrectly here. I'm going to blame Patrick for that one because I copied this code from him. Sorry, Patrick, if you watch this video. All right. And then just so we know that it's done doing what it's doing, I'm going to put in just a blank print line. So that way, if I call it again, we'll have a blank line in there. I think I'm about ready to run this. I'll give you guys just a second to type in this code quickly. But the format, I mean, these if statements are all basically the same. We're just changing the names of the coins, right? So not too hard. I'm going to come out one zoom level here, and then I'm going to hit the run button. And then we hard coded this in, mind you, right? So change for 2.59, $2, 2 quarters, 1 nickel, and 4 pennies. Is that correct? Yes, it is. Now, the next thing to try, of course, would be to throw different amounts in. So maybe how about like $34 and, you know, that's kind of an odd amount, but let's just go $3.78. And then let's do $1.11. And maybe it makes sense to do something weird like that. Try a few different values. You can use the same values as me if you wish, that's fine. But let's see if it does them correctly. That's really the point. So running it. All right, so we know this one's right. Change for 3.78, $3, 3 quarters, 3 pennies. Notice how it's not showing the coins that we don't need. That's the point of this. Right? It's even better than a cash register telling you how much to give back, because you know human beings then have to figure that out. That's why those, if you ever go to like a place that has a cash register where the coins come out automatically, they do that so that people don't screw up the drawer, right? Because they have this algorithm running inside the cash register that drops the right number of coins. Change for $1.11. Yep. Change for 23. Looks good to me. So not only does it give you the correct coins in the correct amount, but it also gives you the most efficient way to make the change at the same time. So this really kind of weird algorithm, I'm just going to get the code back up on the screen here, right, is, I'm going to call it the classic algorithm for making change. Floor division followed by modulus, floor division, modulus, floor division, modulus, floor division, modulus, and then just regular division to finish it off. And then a few if statements to display the stuff that returned a value instead of the stuff that didn't. And you have to give kudos to whatever geek first figured this out, because this is pretty, all our cash registers run off of this stuff. It's crazy, right? With this, here we are in our second week of the Python class, and you're learning some really powerful code. This is powerful code, you guys. Now, granted, if I tasked you to do this on your own, this would be much more challenging. That's why it's guided, right? I don't think you guys would be ready to maybe develop this logic on your own. This is more like a advanced, like second level course kind of stuff in terms of logic. But in terms of seeing how code works, looking at, if statements, floor division, modulus, rounding, the logical flow, being able to come up with a very specific type of real world problem with a real solution. This is some powerful stuff. And I don't know if you're feeling that, but I'm pointing it out so that you are hopefully feeling it eventually, right? So that's basically the solution to lab number 2. All right, so I'm going to let this recording keep rolling here. We're going to move forward, and I think I covered all the parts of the lab, and maybe I should check here. It is asking us to prompt the user, so you know what? Let's do our due diligence and add that to it. So we had some hard-coded values here that we tried. We proved that they work. So if you want, you could comment those out, and then we could write a prompt to let the user enter a value. And then here I'll say, we're testing. Prove it works. Now, back at the margin here, we'll prompt user. So let's do it like this. Let's go right directly to a print statement. So I'm going to build this inside out, because this is how my brain works sometimes. So I'm going to prompt them, and I'm going to say, enter an amount that needs to be converted to a float. Open and close parens. And then we're going to print that. And in fact, I don't need to really do anything else, because, well, actually, so this is the thing. Where am I calling the function? Well, I got to call a function. That's what I meant to do instead of the print. So we would calc change and then put all of this into it, right? Because the function takes care of the printing too. All right. Enter the amount to make change it to a float, send it to the function. Function does the output. All right, let's try it. All right, here it goes. And you know what? We can put in a value that we know, like 2.79. Looks good. And so I think we checked all the boxes now, and I think we learned a whole lot in the process, hopefully. I think I'm going to probably stop this video here. This one's getting a little long. And then for the next lab, I'll start a fresh video.